This is a lesson for pre-calculus for section 1-2. The first thing we want to do is grab our yellow concepts sheet so that we can rate ourselves before the lesson, because we've got quite a few objectives here coming out of section 1-2. I can represent functions numerically, graphically, and algebraically. Been doing that pretty good so far. I can determine the domain. We find out about a new kind of domain here, implied and relevant, and the range of a function. I can determine if a function is continuous or discontinuous and the type of discontinuity. Removable, non-removable, jump, and infinite. That'll be new stuff. I can determine if a function is increasing, decreasing, or constant. I can determine if a function is bounded or unbounded. I can identify local and absolute minimums and maximums. I can determine a function's symmetry. Is it even, is it odd, or is it neither? And then it continues on another page. I can determine if a function has any vertical or horizontal asymptotes. I can analyze the end behavior of a function. So obviously we have a lot of objectives in this section. And some of them, as we go through, you're going to say, yep, I remember talking about that before. Others are going to seem like brand new concepts. You know, in chapter 1 is where we do start to see some new material. So we will be able to represent those functions numerically, graphically, and algebraically, determine the domain, both implied and relevant, and the range of a function, determine if a function is continuous or discontinuous, the type of discontinuity. You probably talked about holes for a little bit last year. Determine where a function's increasing, decreasing, or constant. Determine if it's bounded or unbounded. Identify local and absolute minimums and maximums. And then we've got this even, odd, and neither symmetry. And determine if a function has vertical or horizontal asymptotes. Analyze the end behavior of a function. If you didn't already, rate yourself before the lesson on all of those, because we're going to start. So we're going to start by talking about a function. And remember, a function is special. A relation is absolutely anything that you can graph. But to be called a function, it has to be special. And a function is a relation between two variables whereby each independent variable in the domain maps to no more than one dependent variable in the range, which basically says for every x, there's exactly one y. Now, our definition of a function at the Algebra 2 level is for every input, there's exactly one output. And that's what this says. The independent variable, the one that we get to choose if we make a table, is the x. And that's the input, which is the domain. What it kicks out is the y, and that's the dependent variable, and that gives us the range. So we're looking here at a type of machine. And what we have to realize is that functions can only take in certain numbers. So what I want you to imagine is that we have some pre-image candidates. Now that's going to be new language for you. Pre-image candidates. And those are our x's. And the first thing we have to do before we try to put them in the function is we have to make sure that that's where they belong. For instance, let's say that this machine is a juicer. You're supposed to put fruits, vegetables, all of that good stuff in the juicer. That's what it can handle. That's what your warranty takes care of. But you have a younger sibling, and your younger sibling decides to put a shoe in the juicer. Obviously, that's bad. The shoe should not go in the juicer. So we have pre-image candidates that we are not sure should go into the juicer or not. And if they can't go in, we shouldn't put them in. Now, that's going to be a new concept for us as we go through here, but that requires a little bit of thinking. Is this something that can go into my function? So again, x, I want to write this over here out of the way a little bit. Our x values are the inputs and the independent variable. Our y values are the outputs and the range and the dependent variable. So we've got a mixture of vocab here. So what we're looking at here is a mapping diagram, and this shows us what's going on with our functions. For this x value, it gets mapped to exactly one y value, and x sub 2 maps to y sub 2. For this x value, x sub 1, it maps to 1 point that's a y, so that's going to be our one output. Then x sub 3 maps to y sub 3, which is one output, and x sub 4 matches to y sub 3, but that is still just one output. So this is a function. For every input, there's exactly one output. If we look at the second one, we see that x sub 2 is still just going mapping to y sub 2, which is great, but here comes trouble. X sub 1 gives you the answer of y sub 1, that output, and it also gives you the output of y sub 3. This is not a function, and the rest of it doesn't really matter. As soon as we find one that maps to two different y values, then we're done. That's not a function. So mapping diagrams can be used to determine if something is a function. But we can define a function depending on what we see. We could use a visual. We can talk about the algebra. There are many different ways to figure that out. So this says defining a function. Does the formula y equals x squared define y as a function of x? And I hope that most of you immediately had this picture in your brain with one little change here. Remember, your book doesn't put arrows on stuff. There's our one little change right there. And then if you use the vertical line test, you're going to find that this passes. If you draw a vertical line anywhere on that graph, it's only going to touch in one spot. So that would be a function. So we would be able to write it as f of x equals x squared. And think of it, do the math with it as if it were a function. So like it says, we can represent a function numerically, graphically, or analytically, which is the algebra that we see over there. For instance, the following all represent the same functional relationship. So if you look at the table, you just see the numbers that we would get if we were graphing this. And typically with our parabolas, we'll have some negatives and some positives, but we just needed a little example here to show, hey, this is a numeric way to show a function. For every input, there is exactly one output to represent that, and then a graphic and an algebraic. Now, these say you try. So we want to determine if the following represent functions, and if they don't, we want to explain why, and this is just using these mapping diagrams. So I would like you to go through A, B, C, and D, and pause the video now and see if you can get these correct. All right, starting back up. What we're looking for is for every input, is there exactly one output? Which would mean for all of our domains here, is there just one arrow that's leaving each one of those? And this one is a yes. For every input, there's exactly one output. Same thing for the next one, and this one drives people bonkers, but no matter what number you put in, you get one number back, and that one number is -6. C is a no-go. Right here. Explain why. 4. What f of, we don't know that it's called f because it doesn't give us a name up there, but we're going to call it for f of 1, that equals 0 and 15. So 2 outputs. And yeah, I wrote too big. I'm not going to be able to fit f in there. There we go, 2 outputs. So pretty obvious one. We've got a 1 straying off with 2 arrows there, and that's not going to work. Now, D is the one that people always look at and say, what on earth? I've never seen one like this before. Well, yeah, we upped the game a little bit. And remember, we said we don't have these pre-image candidates. But sometimes we know they can't go into the juicer because they are a shoe. That's what 16 is. 16 was a pre-image candidate that did not go through the function. So basically I need to ignore that and I need to look at all the other points. And all the other points for every input have exactly one output. So this is our pre-image. And that pre-image did not go into that function, and that's why we don't see an arrow leading away from it. So that's new. Then we go to E, and it's changed up. They're not mapping diagrams anymore. Now they're ordered pairs. So go ahead and try E and F. Again, you can pause the video. All right, for E, hopefully you took a look at this right away and said, nope, right there. So this is a no. And to be specific, we could say there's the problem right there. 6, 1 and 6, -5. So it has 2 outputs. And then for F, first 2 of them show an input of 5, and we have 2 separate outputs. So this is a no. 5, 0. 5, -2. 2 outputs. No go. Now, for any of these, we could graph them and use the vertical line test, and we're going to see that they fail. But there's more than just the graphing way to find out whether or not a function is defined by what we see here. So this one says seeing a function graphically. Of the 3 graphs shown, which is not the graph of a function, and how can you tell? So pause the video, go ahead and find the one that they're talking about. Pretty obviously, C is going to fail the vertical line test. If we draw a vertical line and it has to work anywhere on the graph, I see that it's passing through 3 different points. So anywhere on the graph, if it's going to pass through more than 1 point, we have to put a no. And we can put no, and then we can say it fails the vertical line test. You can't just put vertical line test, because you have to explain, hey, this isn't working. It does fail the vertical line test, and the vertical line test says if it's a function, for any vertical line that you draw on the graph, it will only touch in 1 spot. Vertical line test, right there. A graph, set of points xy in the xy plane, defines y as a function of x if and only if no vertical line intersects the graph in more than 1 point. So to pass the vertical line test, it has to just hit once. And if it hits more than that, then it has failed the vertical line test. Example 2 says, determine if the following represent functions. If not, explain why. So again, pause the video, go ahead and do those 6, and then start it back up. All right, so A is a yes. That would pass the vertical line test. B is a no. And this is a fails the, and let's just put VLT, just like a BLT, but with a V. C, that's a yes. That will pass the vertical line test. D, that's a yes. That'll pass the vertical line test. E, that's a yes. Passes the vertical line test. And F, at first we're like, oh, I don't know, does this really pass? Because what happens if we draw a vertical line right there? And then we realize this was a closed dot, but this was an open dot. So it will only touch in 1 spot, because this open dot down here means we can't include that point. So this one is a yes. So we had the 1 no up there in the middle, but the rest of these all passed the vertical line test. Now, in order to graph the equation, you have to have the equation explicitly solved for y. That means you have to have y all by itself. So this means you have to have y by itself on one side and the expression on the other side with no y's over there. So we have to figure out how to get y all by itself. We want to make sure only one value is going to come out of that y. So determine if the following represent functions. If not, explain why. Well, we just said we have to have y by itself. So we would have to subtract 3x from both sides. And you could write it as 6 minus 3x or negative 3x plus 6. Makes no difference, but here comes the biggie. We would have to take the square root to solve this. And we've talked about this before, that whenever we physically write down that square root symbol to solve, then we have a positive and a negative. So that tells us we have 2 outputs here. So determine if the following represent functions. This is a no. It is a no because it has two outputs for most inputs. Now, quick challenge question. For what input would this have just one output? If you answered 2, you're right. Because if we put a 2 in for x, that would give us negative 6 plus 6, which is 0. And 0 is neither positive nor negative. It's neutral. So it could have just one output. But like I said, for most inputs, it's going to have 2 outputs. Now let's take a look at B. For B, I want y all by itself, and I realize there are 2 terms that have y in it. So I'm going to have to get both of those on the same side, but I'm going to have to subtract the 4 and move that piece over because there's no y over there on the right. Now I somehow have to figure out how do I separate the y. And since it's in both terms, I need to factor that out. And factoring is really the name for the distributive property used backwards. So, normally we would distribute that y through to get it out of parentheses there, but in this case we want that y separated, so we're really using the distributive property backwards, which is factoring. And then we'd have to divide both sides by 2x squared minus 8. And I realize that at no time did I have to take an even root here, so I didn't have a plus or minus or anything like that going on. So this one is perfectly fine. It's just y to the first without a plus or minus. Now, for C, this is one where we are supposed to figure out how we're going to get this y business all by itself. So we look at C, and we've got y to the 4th. Oh, well, to get y all by itself, we would have to take the 4th root of both sides. But just as with square root, we have to put a plus or minus. Anytime we do an even root, we have to put a plus or minus. So this one is a no. So any even roots, we have to put the no. Then for D, well, for D, y is almost by itself. If it weren't for that square root piece, I've got to square both sides to solve for y. Well, that's still one output. Again, no plus or minus, nothing funky going on there, so that one is a yes. Oh, I forgot to put the y. It did say explain y up here. Yep. If not, explain why. And again, we want to put for most inputs, there will be 2 outputs. We know there's a couple of numbers that if we put them in there for x would make this 0, and those would be the ones where you would only have the one output. So those are your special cases. Now, domain and range. Note, when a function is described algebraically, use the formula to determine the implied domain. So that means we're just using the math. We're trying to figure out what can we use here. For instance, if we have the square root of x plus 4, we realize that, well, I can use 0, and I can use any positives when I have to find square roots to stay in the real number system. So I would subtract 4 from both sides, and x would be greater than or equal to negative 4. So negative 4 to infinity. Now that's the implied domain. The problem is we don't know if that came from a real-world situation. So the second part of this is if the formula is being used to model a real-world situation, then we need to use what's called the relevant domain. In a word problem, we have to think about what kind of numbers will be going into the formula. For example, we can define the volume of a sphere as a function of its radius by the formula v of r equals 4/3 pi r cubed. And like it says, note that this is v of r, not v times r. It's v of r, it's a function. This formula is defined for all real numbers, but the volume function is not defined for negative r values. Yeah, you can't have a negative radius. It isn't going to happen. So if our intention were to study the volume function, we definitely would restrict the domain and say r has to be greater than or equal to 0. So you're trying to teach something about volume to somebody that's really young, and you realize, yeah, the only way that I'm going to be able to explain this is if I'm talking about the positive numbers, because that's what a radius would have to be. Otherwise, this volume wouldn't even exist. That's relevant domain. That's real world. So if we're dealing with word problems, we want to think about that domain. To find the domain of a function algebraically, we must look for values of x that don't work and exclude those from the domain. Two things we watch for. Are we going to end up dividing by 0 if we put a certain x value in? So this happens whenever we have a denominator that we have to think about. Okay, there's division here. Is it possible that this would make me divide by 0? Taking an even root of a negative number. Can't do that. 0 on up to get our real numbers. And then, number 3, we're not going to worry about this one for quite some time, but that's taking the logarithm of a non-positive number. In fact, you know, that's one of those things later on where we go back and say, yeah, that makes perfect sense. You can't take the logarithm of a negative number. But like it says, we won't worry about this last one until much later in the year when we do some studying of logarithms. We're going to be studying a little bit of logarithms in section 5, but just graphical representations. Now, we want to find the domain of a function. And like it says, express it in set notation and interval notation. We want some practice at both of those. So I look at a, and I realize, oh, I have a square root. So x plus 3 has to be greater than or equal to 0. Because again, I can take the square root of 0, I can take the square root of positive values and stay in the real number system. So we'd subtract 3 from both sides. And then we'd have to go ahead and think about how our answer is supposed to be represented. So if we want set builder notation or set notation, we're using x as our variable. X is defined as x needs to be greater than or equal to negative 3. And there's our Richard Nixon brackets again. So set builder notation has those Richard Nixon brackets on each end, and one line there telling us is defined as. And then interval notation. Think about the number line. You're walking along the number line towards 0 from the left. At negative 3, you realize I can use negative 3, and that's going to be something that needs square brackets because we can use it. And then we'll continue on forever in the positive direction. This one has both of the number 1 and number 2 restrictions that we talked about for the domain. First, it has a denominator that is possible that it would become 0. So x minus 5 equals 0. We'd have to add 5 to both sides and put a can't be equal to right there. And then our numerator has the square root of x. Well, then x is going to have to be greater than or equal to 0. So this is a two-parter, and we need to write it in set notation. Here's our set builder. We used x. It's defined as. Well, there's two pieces, and I think on the number line, oh yeah, 0 comes before 5. So x is greater than or equal to 0. And then how do I tell someone in set builder notation that there's a little bit more information coming? And how we're going to do that is we're just going to use a comma. X can't equal 5. And another set of Richard Nixon brackets. So we don't use a word in there. We just say, you know, here it is. X is greater than or equal to 0, but don't allow that to be 5, and things will be fine. So now think number line, because we're going to do our interval notation. And I realize, well, 0 would be the first good number that I have, but then I'm going to encounter 5. Can't include 5, because that would give us a 0 in the denominator. I'm going to have to jump over 5, so there's my union, and go on the other side of it, and continue on forever. So our square bracket there is at 0, everything else open. C says a of s, and we have the square root of 3 over 4, s squared. And that's actually formula for the area of an equilateral triangle, where a of s is the area of the equilateral triangle with sides of length s. And now what we have to do is think about what is this going to look like. So first things first, let's write it correctly, like so. And so with this one, we think, well, wait a second. If this is just math, then they can use whatever they want because the S is going to be squared. But we have to think when there's a word problem about relevant domain. And relevant domain says, think about what you're doing here. They're not going to be able to put a negative number in for S. That's not going to work. Well, they could put 0 in. You know, it'd be kind of silly. You've got an equilateral triangle with a side length of 0, but they could. So S is going to have to be greater than or equal to 0. And then in our set builder notation, we would say S is defined as S is greater than or equal to 0. And then we would go ahead and do our interval notation by saying, okay, I'm going from 0. 0 is fine. I can put a 0 in there. But then I'm going to the right for my positives forever. And that would be the interval notation. So the implied domain on this one is, hey, it can be whatever you want it to be. But once we read the problem and we know this is about an equilateral triangle, well, then we have to quit that thinking. And we have to start saying to ourselves, no, I know better. I know that it can't have side lengths that are negative. And that is the relevant domain. Now, we are at example 3. And you're going to notice this next page, front and back, all about all this good stuff that we have to do with domain and range. So extra example 3 says find the domain of each of the following, state your answer in set or interval notation. So here's my challenge to you. What I would like you to do is try to do it on your own, and then pause the video, try and do it on your own, and then come back afterwards and see if you have the same answers. For A, I notice there's no square roots, no even roots, but there's definitely a denominator here that might be a problem. And there's no greatest common monomial factor, so I'm looking for two numbers that multiply to -6 and add to 1. And that would be +3 and -2. So again, you can quickly do FOIL on that and see that that would come out to be x squared plus x minus 6. So now, the x in the top is not a problem. That can be whatever it wants to be. My issues are, is there the possibility that there will be a 0 in the denominator? Are there any even roots? Well, yeah, there could be zeros in the denominator because we can't have it be -3 and we can't have it come out to be 2 because -3 plus 3 would give us 0. That would be a problem in the denominator, and 2 would be a problem in the denominator. So now what do I need to do? Well, I need to have my set builder and my interval notation. And I want to introduce you to a new notation that we use for domain. It's just a capital D, and since this one is called f of x, we would say it's the domain of f. And typically I'll just put a colon there because that's just describing, hey, this is what we're going to write down for our domain of f. Now, we have x's defined as, and we want to tell people, hey, you can use whatever you want, but you can't use -3 and 2. And that's exactly what we're going to tell them. X can't be -3 and x can't be 2. And that's the set builder notation way to write it. A little different, a little more involved when you think about the number line, because we're telling people, come on in from -infinity, but when you get to -3, you got to jump over it and get back on the number line. Then you're going to hit 2. You got to jump over that as well. You can't use it. Everything else is good. So it gets to be a little bit longer interval notation than we're used to. For B, we have 3 times, or I'm sorry, here I am starting to factor it already in my head. 3 is the common monomial factor to my numerator, so I can go ahead and take the 3 out by factoring. And then in the denominator, that's a difference of 2 squares, so no greatest common monomial factor, but it is a difference of 2 squares. Now, there's a reason that we had to factor everything, and that's because occasionally we get to a spot where we're going to start talking about the graphing. And when you have a factor that will be canceled out on the top and the bottom, numerator and denominator, then you'll actually have a hole in your graph. Now, this isn't about the hole right now. What this is about is us figuring out what numbers we can and can't use in this. And that simply speaks to the denominator. So this one would be capital D of G, since this function was named G of X. And we'll put it in our set builder notation in just a minute here. I'm going to start by just writing over here X can't be plus and minus 4. So set builder, X is defined as, and again we could just say X can't be plus or minus 4 and Richard Nixon brackets. And yes, we can write it as plus and minus 4. Anybody that knows any math will be perfectly fine with that. So now, on the number line, we're at negative infinity. We're going to hit negative 4. We've got to jump over it, get back on the number line. We're going to make our way to 4, jump over it, and then on forever to the right. So like I said, later on when we are graphing this hyperbola here, we're going to be talking about, where's the hole located at? But right now, it's just about the domain. H of x. So for h of x, I see that I have a square root. No denominator, but I know that 2x minus 3 has to be greater than or equal to 0 in order for this to work in the real world. So we'd add 3 to both sides and divide by 2. And this would be the domain of h. So we're going to describe this in set builder notation by saying x is defined as x needs to be greater than or equal to 3/2. And another set of Richard Nixon brackets right there. And in interval notation, walking on the number line, we hit 3/2. 3/2 is good, and we can go to the right forever. And that's going to be our interval notation. For D, we have another square root. No denominator to worry about, but another square root. So the square root of 3 minus 5x, we know 3 minus 5x has to be greater than or equal to 0. So we'd subtract 3 from both sides, and we would divide by negative 5. Now dividing by a negative with an inequality means you have to flip the sign. So x will be less than or equal to 3/5. Now, we need that in set builder notation. So D of P, x is defined as x is less than or equal to 3/5. So now I start thinking. Interval notation. So my domain is going to say, hey, you can use all those fancy-dancy negatives down there for negative infinity, but you're going to get to 3/5, and you have to stop, because 3/5 is the last number that you can use there. So that would be our interval notation. So only 2 things we're watching for on the whole page. Denominators being 0 and even roots. Well, this one has both. All right, so y equals the square root of 2x minus 1. Why am I rewriting it? I'm really hoping that I can factor that denominator and figure out what would make it 0. We don't have a common monomial factor. It's not a perfect square trinomial, but there are 2 numbers that multiply to negative 10 and add to negative 3, and that's going to be negative 5 and positive 2. So now I have all kinds of things to look at. I know that x can't be 5, x can't be negative 2, and I know that 2x minus 1 has to be greater than or equal to 0 because I had both of the conditions that we were looking at earlier. So I'm going to have to add 1 and divide by 2. And dividing by a positive 2, I don't have to do any flipping, and I just wrote the 2 down because I said 2. There we go. So x is greater than or equal to 1/2. Now, this we have to think about a bit, because x is greater than or equal to 1/2. Wait a second. I'm never going to be able to use that negative 2. Yeah, that's okay. It's not relevant to the problem. I mean, if x has to be greater than or equal to 1/2, we're never going to mess with that negative 2. So we don't want to tell people about that. And unfortunately for this one, it did not name it as a function, so we're just going to have to put a capital D here. Now, our x is defined as, well, we said x has to be greater than or equal to 1/2. but there is going to be one bump in the road. 5 on the number line. So we have to put comma, x can't be 5. But we need to leave that -2 information off of there. Otherwise, that says, oh, we didn't recognize that x has to be greater than or equal to 1/2. So now in interval notation, we'd have to start by saying, all right, got to be greater than or equal to 1/2. So here's my 1/2. Ooh, but as I walk on the number line, I'm going to get to 5, and I'm going to have to jump over 5, and then I can get back on the number line. So interval notation is fantastic for making you think about the number line, and that's what we absolutely have to do. Love that problem. It's got so much going on there. Alrighty, now for F. Well, numerator's okay. That can be anything it wants to be. But my square root of 4 minus 7t, that's going to need a little of my attention. So 4 minus 7t has to be greater than or equal to 0. Oh, wait. No, it can't be equal to 0. It's in the denominator. So here's another one where we actually have both situations at one time. It's just that it seems kind of hidden because the square root is the denominator. So now we'd have to subtract 4 from both sides. And we have to divide by -7, which of course means we have to flip the sign. So t is going to have to be less than 4/7. So definitely a thinking problem. You start by thinking, wait a second, I've got my square root. It has to be greater than or equal to 0. Oops, it's in the denominator. It can't be 0. So then you switch gears. So this will be the domain of M, and it's the set of all t. We have to use t because that's what they used, where t is less than 4/7. And another set of Richard Nixon brackets over there. And then in interval notation, we'll go from -infinity to 4/7, but we cannot include 4/7 because, again, that would make our denominator equal to 0. So we have to watch out for those little things, I guess it's tougher to think about both instances happening at once, that we're dividing and we have a square root, but we have to keep that in the back of our mind. G. Alrighty, for G, we've got a square root up there, so -x has to be greater than or equal to 0, but if we divide both sides by a -1, we'll have x is less than or equal to 0. Alright, so that's the first part of it. And now I need to figure out when will x squared plus 5 equal 0. So the first thing I did was said to myself, that is not factorable. There's no greatest common monomial factor. It's not a perfect square or anything. So I'd have to subtract 5 from both sides and then take the square root. But that's kind of weird, because that's going to be plus or minus the square root of 5i. That's actually good news. It means there are no real numbers that will make that denominator equal to 0. And if you think about it, you'll see that, because you're putting an x value in and you're going to square it. So it's going to be positive no matter what. There's not going to be a chance that we're going to be able to get 0 out of that. So we're talking about real number domains, and this one did not, unfortunately, give us a name. Set builder notation, we have an x for a variable such that x is less than or equal to 0. And then we have to go ahead and put that in interval notation. So that's going to be -infinity up to that 0. And including that 0 is just fine. So as I'm getting to h, I look at it and I think, oh, that's a double whammy. That is definitely a double whammy right there. I've got a denominator that could possibly be 0, and I have a square root. So I do notice that my numerator is going to be factorable, and it's never a bad idea to do that. But there's no way that I am going to see the same factor in the denominator, so we're not going to have a whole. So our time needs to be spent right here. 3 plus 5x squared needs to be greater than, oh wait, can't be equal to. Remember, that's what happens whenever we talk about having our square root in the denominator. Alright, I'm going to have to subtract 3 from both sides and divide by 5. And then I'd have to take the square root. Well, that's going to be x is greater than the square root of 3/5 I. Well, what does that mean? Well, it's imaginary. That's the only way that we would get a 0 in the denominator would be by having that be imaginary. And again, our domain is about restrictions for the real world. So what that means for us is this one doesn't have any restrictions. Now, just so that everybody remembers that we really, normally shouldn't leave that square root of 3/5, what we would want to do is say it's the square root of 3 over the square root of 5, and we would want to rationalize the denominator, like so. But in this case, it was just the fact that we had to figure out that it was plus or minus the square root of 3/5 here. All right, so now, like I said, it's imaginary, and so what we do at this point is say, okay, well, there are no restrictions. So how do you say that when you're talking about x? Well, you just say it's the real numbers. And remember, the capital R with the extra line on it is going to stand for real numbers. Then, interval notation, even easier. Use whatever you want. Negative infinity to infinity. All right, looking at I see that I have a square root, and that's in my numerator this time. And I have some possibilities for some zeros down there in the bottom. So I don't want to forget to do everything I need to do. F of x equals the square root of 5x minus 3 over. And I'm looking at it and thinking there's no common monomial factor here. Not a perfect square trinomial, but if we do x plus 3 and x minus 1, and you FOIL that back together, you'll see that you have x squared minus x plus 3x, which is 2x minus 3. So now I focus on my square root. 5x minus 3 has to be greater than or equal to 0. It's in the numerator this time, so it has to be greater than or equal to 0. And then I would add 3 to both sides, and I would divide by 5. Now, often, these are situations where you have an answer that you don't end up needing. It's not relevant to the situation. We had some zeros down here, and that's going to be negative 3 and 1. But now I realize, well, I was never going to get to negative 3 anyway. I mean, for this to work, x has to be greater than or equal to 3/5. So that means we don't need to use the x is not equal to negative 3 at all. So domain of f for this one, set of all x, such that, and we'll say x has to be greater than or equal to 3/5, but don't let it be equal to 1. And that will take care of it. Because on the number line, we're not going to worry about negative 3. We're never going to be there. We're going to be a positive 3/5 and moving to the right forever. And then we go ahead and write it in interval notation. And we're going to start at 3/5 and include it. And then we're going to be walking on the number line and we're going to hit a 1. And we're going to have to jump over the 1. And then to infinity. I always want to say to infinity and beyond. Alrighty, let's take a look at J. Okay, cool. No variable in the denominator. That means we don't have to worry about that part, about dividing by 0. It does have a square root, but hey, the x isn't even under the square root. Well, that means we can use whatever we want. The domain of f, set of all x, such that x is all real numbers, negative infinity to infinity. Cool beans! No work with that one. All we had to do was figure out that, hey, everything's going to work in here. So when your variables are under the square root, when your variables are in the denominator, then we have to worry about restricting the domain. Alrighty, we have p of x equals 4. Ooh, square root of x squared minus 4. Minus 4. Yikes, there's a lot going on there. Okay, well then, x squared minus 4 is going to have to be greater than or equal to 0. At least there's no denominator, huh? And then I'd have to add 4 to both sides. And then I'd have to take the square root, but this is an inequality. How does that affect this? Well, because it was x squared and it was never going to be something that would be negative after we squared it, we have to let people know that. And use that absolute value symbol. So the absolute value of x has to be greater than or equal to 2. And if you're worried about, well, what happened to the positive and negative piece? That's going to be taken care of in just a minute here. Because we have to remember that we're talking about something whose distance from 0 is greater than or equal to 2 units. That graphs out to the extremes. So x will be less than or equal to negative 2, or x will be greater than or equal to positive 2. And we have to be careful with that when we have something that's even for powers, an exponent that's even underneath an even root. And that's what happened here. So we have to think our way through those pieces. So d of p, set of all x, such that, well, what we just said, x is less than or equal to negative 2, or x is greater than or equal to positive 2, and all because it was an x squared underneath that even radical right there. And then in interval notation, well, we're walking down the number line from negative infinity, but we're going to get to negative 2 and we're going to have to stop. So we can use negative 2, but then it's back on the number line using 2 and on forever. So there's our interval notation piece for that. So that one's pretty unique, where we had the variable squared underneath a square root. So then that brings us to m of x. So problem L that has the m of x. And we have the square root of 4 minus x squared. And again, I'm thinking about it right away. Okay, got to be careful here. That has that squared business in there. And that has to be greater than or equal to 0. Don't have any denominator to worry about, but I've got to make this happen. So I'm going to have to subtract 4 from both sides. Then I'm going to have to divide both sides by a negative 1. Oh, that means I have to flip the sign. And now it says x squared is less than or equal to 4. Oh. Well, then I'm going to have to do the absolute value when I take my square root. Less than or equal to 2. But less than or equal to, that's the stuff that's sandwiched in. So there comes my negative. Remember, we don't worry about that until after we've dealt with that absolute value. So for this graph, we're going to have to just graph between negative 2 and 2 for the x's, and that's absolutely right. The domain of M is going to be the set of all x, such that x is greater than or equal to negative 2, less than or equal to positive 2. Have to be set up in order according to the number line. All of my answers here have been. And then we realize, well, that's going to be a quick little interval from negative 2 to 2. Now, for K and L, we actually want to take a look at these on the graphing calculator, and we want to see why they have such a weird domain. I didn't want to make you watch while I type this one in. This is K, which had P of x equal to 4 square roots of x squared minus 4. The whole thing minus 4. So let me hit zoom 6. And let's see why this one has such a... Oh my goodness, look at that crazy business going on there. But it is exactly what we said was going to happen. We said, hey, you can use from negative 2 off to negative infinity, and you can use from positive 2 out to positive infinity, and that's exactly what happened with this. And again, it's because we had an x squared underneath our square root, and when we graph, that's just crazy. So I'm going to pause it again and put in L, which was the m of x piece. So now we want to take a look at this one, which all it did was it reversed the order of the x squared minus 4 to 4 minus x squared, so basically multiplying it all by negative 1. But let's take a look at the craziness of this one. Zoom 6, and look at that. Our entire graph, our x values are between negative 2 and 2. which is what we said absolutely should happen. And there it is. So graphically, great way to verify that you have done everything correctly when you're talking about the domain and range too. That works out nice. Now, that's enough because I should let you know that example 3, we usually don't go through all of these in class. I wanted to give you the advantage of seeing every single one of these since you're not in the class, and it's hard to do this when you're not in the classroom. So all of these were on here. And yeah, this is a long section. You should notice that from all the concepts that we had. Here is a little homework to get you started on 1-2 here. Just number 1 through 20 from 94 to 98. So lots of good stuff. Tons and tons of really great domain stuff. Talking about a new concept of pre-image. We really hit a lot of those concepts really hard. So I don't know, you might want to rate yourself after the lesson for the ones that you feel were covered in this so that you can have some of those done. There were a lot of objectives here.